same page if there's no kind of specific questions. Let me find, well, maybe it would be a good one here. So remember, again, it is sometimes what gives people a very difficult time is these drawing sort of the products of these reactions. And, it's because sometimes people want to kind of make things more complicated than it has to be. And the important thing to remember is when we talk about any of these type of different reactions throughout sort of all these organic sort of functional groups and chapters and stuff like that is, there's always only really one part of the organic molecule that will change. And here, when we're dealing with the double bond, it's always just the double bond that will change, especially when we're adding two things to it. Again, as we talked about, it could be a symmetrical addition, like any of these guys. And again, symmetrical just means, hey, we're just adding two of the same. Or again, you have this double bond, no matter how many carbons are on either side of it, these sort of unsymmetrical additions, which would be something like water, something like HCl, HBr. They all pretty much always do the same thing. And what happens in all these sort of alkene reactions is very simply, all you have to do is, like we did, just recopy it, turn those guys into a single bond, and then really one thing goes over here, one thing goes over there, one guy goes over here, one guy goes to this carbon. It doesn't necessarily have to be drawn upwards, but it just gets attached to those carbons, so this is like one thing, two things, those is where those things go. Same thing here. The only thing is, again, when these sort of unsymmetrical additions, like we were talking about at the end there, if you have options for that hydrogen, again, it always ends up at the carbon that started with the most hydrogens. And that's actually what is referred to as, well, I was butchering the name, I probably still will, Markovnikov's rule. Actually what that's called. So, you don't want to make it over complicated. And the other thing that sometimes people incorporate into sort of their products is these catalysts. And again, if you can recognize something as a catalyst, most of the time it will be drawn on the arrow. Sometimes it might not. It might actually be kind of written to the left, but most of the time it'll be on the arrow. Again, those things really don't really participate in anything. So why don't we try a couple more here just to make sure. So let's do this here. Let's add H2 and a nickel catalyst. So draw the product of that one. Let's do draw the product of what you get as a result of that one. Let's do something there. And lastly, we'll do this guy. Okay, so for each of them, draw the product that you should get. So take a few minutes here and see what you come up with, and then we'll talk about it. Okay, so let's take a look and see how you're doing. And again, I say this this way to to make you not overthink it. And these really should take you very quickly to sort of draw these things. And if you do it that way, it probably means, again, you're not going to overthink it and do some weird things. Again, the important thing is really, if you think about it, you pretty much have the structure you need. It's actually already drawn for you on the left-hand side. You pretty much just need to redraw it on the right-hand side and really change really just the part that needs to be changed. So in all these cases, because these are all addition reactions, and every single one of these molecules that are here, it's really only the carbon-carbon part that changes. You know, everything else pretty much stays exactly the same. And the way it changes is it's going to change the exact same way every time. We're going to basically make that double bond into a single bond. And the purpose of that is so that we can allow space for, in the first case, each of those hydrogens to be added in. In the second case, each of the bromines to be added in. In the third case, the hydrogen and the OH to be added in. And in the fourth case, the hydrogen and the Cl. Remember, as it sits right now with that double bond, it doesn't have room. It doesn't have room for those guys to come in. So basically, we're just kind of making space, if you will, for those guys to come in. So again, you don't want to overthink it. You pretty much just want to, copy what's here. So again, that's what I'm going to do on the other side. I'm simply going to copy exactly the way it looks. I could even keep the way it's drawn and sort of the structure there. The only difference is I'm now going to turn my double bond into a single bond. And again, you can see absolutely nothing else really has changed. And like we talked about before, by making that double bond into a single bond, we now have space for each of these guys to be added in. They are going to be added into different carbons. You can't make a mistake here because this, again, is a symmetrical addition, which means you're adding two hydrogens, which means you could put a hydrogen here, put a hydrogen here. And that would be it. Yeah, you can straighten it out if you want, but I kind of kept the same sort of structure. Any questions on that there? Now going to our second one here, again, I'm going to do the exact same thing. I'm going to simply just redraw exactly what I got going here. And again, that means I have a CH3 that's attached to a carbon. That guy also has a CH3 coming down from the bottom. Here I'm at my double bond, which I'm now going to turn into a single bond. I'm just going to change it up a little bit. I'm just going to draw that H. So that's this H right here. I'm just going to draw it down just for clarity purposes so you can see where things are going. And our CH3. So again, exactly the same. Only difference is I just drew the hydrogen out here. That again, hopefully will better allow you to see that we have now opened up room right here on each of these carbons. Again, in this case, one carbon gets a bromine, other carbon gets a bromine. Again, a symmetrical addition happening here. We're just going to simply draw the bromine in there and draw the bromine in. Question on that one there.
Do both the bromines have to be on top, or can they be diagonal?
Honestly, because this is an alkane, you could have drew them down. You could drew one up, one down. It's all the same, to be honest with you. Again, because we don't have any double bonds like we were talking about in terms of locking guys into one or the other. You could draw like I did, both up, both down, one up, one down. Obviously, if you did them both down, then these two guys would go up, in terms of locations.
Okay, thank you.
You're welcome. Other questions? Okay, so continuing on with this pattern, and hopefully you could kind of see a pattern of I pretty much have 98% of my structure right here if I highlight the whole thing here. So again, going to do the exact same thing. Not going to play with anything. I'm just going to recopy what is there. Again, I'm now coming to my double bond, which I'm going to make a single bond, kind of wobbly single bond. Just like I did before, just for clarity purposes for you guys, I'm going to draw this H down. So you can again kind of see what's opened up. That then leaves me my CH2, my CH2, and my CH3. Again, you can hopefully again see the two spots that are here. Now, this addition here is going to open up the spots for our hydrogen and our OH group. But this is an unsymmetrical addition that involves hydrogen. So there is a thing that we do have to worry about, and it is the placement of the hydrogen. Remember that when we have a hydrogen in something else, the hydrogen should end up at the carbon with the most hydrogens to start with. So you could look at the one you drew to the right, you could look at the one you drew to the left, and we're talking about the two carbons that are in a double bond. So this carbon originally directly attached to the carbon has no hydrogens. This carbon on the right has one hydrogen attached. You can maybe see it better over here on the right-hand side here. Again, we have the one hydrogen attached, directly attached to this carbon, no hydrogens. So based on Markovnikov's rule, that means that the hydrogen should end up over here on the carbon that had the most hydrogen to begin with. The OH would then end up on the other carbon. And this would give us, as we were talking about last time, what is referred to as the major product. And here we actually just produced an alcohol. The OH group is the functional group for an alcohol. Question on that one. All right. And lastly, here on the bottom, it's worked so far for the first three. Minus will continue the same sort of approach. Again, we're going to simply draw this thing exactly identically to where we started with. And again, the only difference is we're going to turn that double bond into a single bond. So without thinking too much, I'm just going to copy basically what's there. Again, I'm going to put that hydrogen down so we can have a little bit more clarity of sort of seeing what's happening. That's going to bring me to my double bond that now becomes a single bond. And, you know, I'll do my H, I'll draw my H's out over here as well so we can have some clarity of what's happening. Those are the two H's that are right there. We can see just like before, we have now opened up our carbons to allow a hydrogen to come in and a chlorine to come in. Again, unsymmetrical addition. Again, we do have hydrogen involved, so we need to make our decision as to which carbon should get the hydrogen. So hopefully from the conversation we just had, you would come back here and look at this carbon and go, it's got one hydrogen attached. You would come to this carbon here and see it has two hydrogens attached. So that means that the hydrogen should end up on the carbon on the right. You could also see the two hydrogens here to start with. The Cl would then end up on the other carbon, and that would be the correct structure there. Any questions on how we got any of those sort of structures? So again, I can't stress enough how, you know, sometimes people overlook the fact that they kind of have the structure already there for them to begin with. So it's really important to, you know, keep that in mind when you're drawing these things, especially when you're drawing reactions. It's not necessarily just this reaction here with the alkanes, the alkenes that we're talking about, but for the most part, most organic sort of reactions like these, where you're asked to draw the product and you have like the starting guy, you know, pretty much gives you almost the product. You just got to realize what is changing, you know, in these different types of reactions. Any questions on these type of reactions here? All right. Any other questions I can answer on this stuff here? Okay. So what I'm going to do is, since we got a little bit of time, I'm going to kind of preview a little bit about alcohols, which is where we're going next on Monday. And again, just to hopefully give you some information on that. And obviously we just kind of touched upon alcohol is actually right here. This guy is an alcohol. So let's talk a little bit about alcohols and just some of the ideas behind, alcohols and sort of what's going on. So first off, though, when we talk about alcohols have the functional group of OH. So just like when we talk about an alkene that has the functional group of a carbon-carbon double bond, or an alkyne that has the functional group of a carbon-carbon triple bond, when we see an OH group on a compound, that becomes the most important thing in terms of that particular type of compound, and it's what really classifies it as an alcohol. That OH group is the same OH group that we see like in water, for example, and it is a polar group, actually. And if you remember from when we talked about bonding and stuff, electronegativity difference, more electronegative heading this way. This guy is more negative. The hydrogen is more positive in terms of that bond. Now, this actually makes alcohols kind of soluble in water. At least small alcohols like 6 carbons or less are pretty soluble in water, because it's able to, when you have an alcohol and when you have water, they're able to actually interact with each other through what is referred to as hydrogen bonding, like we talked about with those intermolecular forces. They're able to hydrogen bond with each other. So this type of organic compound does have some solubility in water because of the presence of that OH group. So it's able to really interact with water. Again, though, if you start building out all the carbons, like get over 6 carbons, 7, 8, 9, 10, 11, 12, 14 carbons, the solubility decreases a lot because there's just that one little spot that can interact with water. But relatively small alcohols are fairly, soluble in water and can interact really well with water. When we talk about alcohols and we talk about classifying alcohols, we could classify alcohols as a primary alcohol, a secondary alcohol, or a tertiary alcohol, much the same way that we could classify carbons. So if you remember, we could classify carbons as primary carbons, secondary carbons, and tertiary carbons. What did it mean when we were classifying carbons? If you remember, it was whatever carbon we were looking at, how many carbons were attached to it, right? So 1 carbon would be a primary. If you had a carbon that had 2 carbons directly attached to it, it'd be a secondary. If you had a carbon that had 3 carbons directly attached to it, that would be a tertiary. Alcohols kind of work the same way. If you have a alcohol, like an OH group, where the carbon that has the OH group attached is attached to 1 other carbon, that would be a primary alcohol. If you have the carbon that has the OH group and it's attached to, as you could probably imagine, 2 other carbons, that would be what is referred to as a secondary alcohol. If you have the carbon that has the OH group attached to it and it is attached to 3 other carbons, that is what is referred to as a tertiary alcohol. So we could classify alcohols kind of like we classify carbons as primary, secondary, or tertiary. And that's really important because depending on the type of alcohol, is it a primary alcohol, secondary alcohol, or tertiary alcohol, it will result in a different sort of reaction or outcome that will happen as a result of a reaction, depending if it's primary, secondary, or tertiary. Any questions on that there? So how do we go about naming these guys, which is kind of an important thing. So naming really, again, as you can imagine, follows everything else we've been talking about, which is what is the first thing we want to do? We want to find the longest carbon chain. This longest carbon chain does need to include the OH group, right? Just like when we did double bonds or triple bonds, the longest carbon chain had to include the double bond or triple bond. Once we do, just like everything else, it will match an alkane. So what we do is we kind of drop the last part of the name for an alkane and make it OL at the end. So this guy ends in OL. So for example, if we had this guy right here, this is one carbon, which is based off of methane. It has the OH group, which tells us it's an alcohol. This would be known as methanol. Drop the last part and put OL at the end of it. So drop that last part, put the OL. We had this guy. This has one carbon, two carbons. Two carbons is based off of ethane. Has the OH group, makes it an alcohol. Ethane becomes ethanol. Sometimes common named, people will call the first guy methyl alcohol. If I spelled that right, alcohol. There we go. Sometimes people will call this guy common name ethyl alcohol. Why do they call that that? Well, that's like a methyl group right there attached to the OH. That's like an ethyl group attached to the OH. This, though, would be the IUPAC way of naming, and the proper way of naming would be these guys. Now, in both of these cases, the methanol and the ethanol, there really is no option in terms of where the OH group is placed. And what I mean by that, obviously in methanol, there's only one carbon, and that one carbon obviously has the OH group attached. Down here, this guy is where the OH group is attached. Your other option would be to put it onto this guy. If you move the OH group over to the second carbon on the left, it would still be carbon number 1. It's really the same thing, no matter which way you name it. If you name that like 1 ethanol, if you moved it to the left, it would be 1 ethanol. So in the case of these two guys, we don't actually need to give the number where the OH group is located, because technically speaking, it's only could be in one place. When you get to 3 or more carbons in an alcohol, you need to give the number of the location of that OH group. So just like we did with the double bond or the triple bond, we need to give the number of where we find the OH group. And we want to give that guy the smaller number, so it is the priority in terms of numbering the chain. So the OH group is really the priority here in numbering. So we want to make sure, like we do with the double bond or triple bond, that OH group gets kind of the lower number. Any questions on that? And why is that important? Well, let's just take a look at 2 examples here and kind of go through the naming process of both of them. Let's say we had, let's do this. I'll just draw it out in more expanded form so we can see everything here. And let's kind of do this guy as well. Okay. Now, if we look at the first one here, we would follow our same steps as we did for naming anything else. We're looking for the longest continuous carbon chain that obviously has the OH group, which it does here. And that is 3 carbons in a row. 3 carbons in a row with an OH group tells us it's an alcohol. 3 carbons in a row is based off of propane. Because it has this alcohol group, we drop the last part and it becomes known as propanol, OL, like alcohol. Now, we need to give the location here of that OH group. We have our same 2 options in terms of numbering. We could go carbon 1, carbon 2, carbon 3, or we could go carbon 1, carbon 2, carbon 3. The OH group here gets the priority, which means the lower number would be 1, which means we would want a number in this direction. We would not want to do this numbering here. That means that we would add that to our name, and this would be what is known as 1-propanol. The 1, much like what we had with double bonds and triple bonds, tells the person the location of the OH group in this case. Any questions on that? Why is that important? Well, if we look at the example to the right and we follow our same steps, longest carbon chain is 1, 2, and 3. That obviously has the OH group there. So just like previously, this would be based off of propane. Because of the OH group, this would be known as propanol. There we go. Now, if we just kept them both named propanol, there would be no way to distinguish between them, right? Because the OH group here is on carbon 1, but in this compound, the OH group is actually on carbon number 2. And this would be known as 2-propanol. So there is a difference between these 2 molecules where the OH group is sort of located. And we do need to have that 2 there again for the location of the OH group. Any questions on that? We would obviously name any other group that would be there based on the location of the OH group, whichever way we decided to number. Side note here, 2-propanol is also known as isopropyl alcohol. Why is it called isopropyl alcohol? Because if you remember when we talked about those alkyl groups at the very beginning, CH3, CH, CH3, that is the isopropyl group, right? And because this is an OH, kind of a common name is calling this isopropyl alcohol. Isopropyl alcohol, 2-propanol, rubbing alcohol, all the same thing. Lots of different names for the same thing in organic chemistry. They have historical names, common names, IUPAC names. So sometimes you do come across different names for the same compound. But you should always go again for the IUPAC way, which would be this name right here, or that name over here. Question on those 2. All right, so why don't you try one here, see what you come up with. All right, so take a second and see what you come up with here. Look, and again, we want to approach it the same way as, everything else. So we're looking again for that longest continuous carbon chain. And in this case, you can't get it 2 different ways. You can go straight across, which is 4. You could also start up on top and hang a right, which would get you 4 as well. So again, you could choose either way you want. Both should give you the same name. I personally think sometimes it's best just to go with the straighter one So you could really identify kind of everything that's going on here. So obviously 4 carbons in a row is going to be based off of butane. Because we do see the OH group, it tells us it's an alcohol. So our butane becomes butanol, OL. It has more than 3 carbons, or 3 carbons or more. So we do need to give the location of that OH group. So we do have 2 options in terms of which way we can number. We can number left to right, which would be 1, 2, 3, and 4. We could also number right to left, 1, 2, 3, and 4. So which way should we choose? Because this is the OH group and it is the functional group, it does get the priority here. So we would want to name it or number it whichever way gives the OH group the smaller number. And in this particular case, the OH group would get a smaller number by numbering it right to left in this case. So that is the way that we would want to number this guy. Again, the OH group taking the priority, and we want to make sure we get it to that smaller number. So going right to left tells us that the OH group is at carbon number 2. So that is 2-butanol. Because we locked in the numbering going in this direction because of the OH group, that means that our other group that's hanging out there has to be numbered accordingly. And that means that that case, the methyl would now be at carbon number 3. So this now would become 3-methyl 2-butanol. Any questions on that name? Is this a primary, secondary, or tertiary alcohol? Take a second and think about which one it might be. Okay, so in order to determine that, we want to look at the carbon that has the OH group attached to it. And what we're looking at that carbon that has the OH group is how many carbons are directly attached to it. So directly attached to that carbon is 1 there. Directly attached to that carbon is 2 there. This would be a secondary alcohol because of that. So we're looking at the carbon that has the OH group attached to it and how many carbons are directly attached to that carbon. Question on that there. All right, so since we're almost done here, one last little thing about alcohol, since we're talking a little bit about naming here. What happens if we have a nice kind of cycloalkane that we decide to put an OH group on? Well, we would kind of approach it the same way. This entire thing would be the base of the name, which would be cyclohexane. It has an OH group, which makes it an alcohol. This then becomes cyclohexanol. No need to name or number the OH group here, because wherever that OH group is in the ring, it's assumed to be carbon number 1. So in this case, you would not need to give the location of where that is because it's assumed to be carbon number 1. Any questions on that there? Now, that's important because if you had the exact same thing, and that was OH, and you had a CH3 attached there, what would this be called? Well, it would do the same thing. Big thing here is our cyclohexane with the OH becomes cyclohexanol. Now, this is carbon number 1. We need to give the number of this guy. If we went counterclockwise, that would be 2, 3, 4, 5. If we went clockwise, 1, 2, and 3. So this would be 3-methyl cyclohexanol. So you don't have to, much like a double bond in a ring type structure like this, you don't have to give the location of the OH group, but it is going to be number 1 in terms of numbering, everybody else numbered accordingly. Again, here giving the group the smaller number. Any questions on any of that stuff there? Okay, so it looks like we're kind of out of time. So hopefully this helped get you a little kickstart on alcohols. Obviously, we'll